We'll then go to our next presentation, where we kind of shift gears. What you heard in the first presentation was largely related to soil investigations. Meyer, who is going to give us a presentation to really talk about a different type of pile foundation that we haven't heard much about in this series, the CFA or the ACIP piles. Matt, take it away.
Thanks, Gerald. Appreciate that. And Sheree, great presentation. You know, a lot of good points, and really interesting to see how you're using the CPT now in addition to other traditional investigative techniques. So without further ado, I'll jump right in here. My presentation today is going to be on the efficiency associated with variable length and capacity CFA and auger cast in place piles. The presentation is going to follow the outline you see here. We're going to talk a little bit about terminology of what's called the single pass rotary system. For those of you who are very familiar with the CFA or auger cast in place pile system, this may just be a review. But for those who are not so familiar, it's important to define the differences and the nuances with the various different systems. We'll talk a little bit about drill tooling and system applicability specific to the two different categories of single pass rotary systems that you're going to see in the next couple slides. I'll then give you a general overview of the auger cast in place or CFA pile installation methodology specific to what I'll call the drilled system and not the screw pile or displacement system. I will then present two mini case studies, one specific to the Mercedes-Benz, where this variable length single pass rotary system was implemented, and another for a beachfront high-rise in South Florida, where a markedly different condition was encountered, which required maybe somewhat of a different approach that you're going to see when you compare the two different kinds of mini case studies or case histories. Important to both of the cases is the pre-delineation of the variable subsurface conditions. I'll talk about the evolution of how we came up with the ideas, the concepts, the approaches, how the capacities were initially thought, the importance of settlement compatibility. Then I'll move into an emphasis on phased and extensive subsurface investigation. And the theme of the seminar, as you know, is testing, testing, testing saves money. And this is very paramount in the approach and application of what I'm talking about today. We'll then move into some load test validation, how that load testing may modify or revise those initial approaches. And then I'll talk about the multitude of applications and varied installation methodologies and criteria that were essential to implement the varied depth, varied length system. And then we'll focus on the importance of how do we make sure in production that we implement the concepts that were envisioned initially and refined in the pile load testing process. And ultimately, how do we have our field staff implement and confirm that the design methodology is properly implemented. And lastly, I'll talk about performance monitoring, which we don't see a lot of, which I think you'll find unique in the mini case history number 2. So just moving now quickly into terminology, as I mentioned, what I'm talking about today is a single pass rotary system. I am not talking about drilled shafts or drilled piers. There's two categories of this single pass rotary system. They are on your left, what I'll call a continuous flight auger system, auger cast in place piles, auger cast or auger pressure grouted piles. That's in the category of the drilled pile, where we're not so focused on the in situ stress state and preserving the stress state in the ground, or maybe increasing the stress state in the ground, as we may see with the category of piles on the right in red and in yellow, which is our European screw piles, drilled displacement piles, intermediate or partial displacement piles. Those systems look at potentially enhancing the lateral stress, increasing side shear resistance through displacing action with specialized bits and tooling as you drill, and I'll say the word drill loosely, as you attempt to screw the pile into the ground. And this next slide, I think, is really going to hone in on what I'm talking about. Is the two categories are drilled CFA or auger cast in place pile or auger pressure grouted piles, and the screwed system, which is our drill displacement, partial drill displacement. And the CFA may be a little bit in the middle when we talk about the European style CFA, where we attempt to twist the auger into the ground, being very cognizant of how much spoil comes to the ground surface. But that's a further in-depth conversation and topic. So I would refer to the folks on this presentation to many of the DFI publications that are available. And I don't want to get bogged down in the terminology or these systems, because I won't have enough time to talk about the interesting things that you've come to listen to today, which are these mini case studies. So the drilling tools, as I mentioned before in the prior slides, we got the conventional auger cast in place pile tooling. We've got the intermediate or partial displacement tool, and we've got the full drill displacement tool with auger flighting below, a displacing element, and reverse flighting above. And again, please refer to various deep foundation industry publications for additional information on these specific toolings and their applicability to various geologic settings. So just a high-level overview of this single-pass rotary system that we're talking about today. So the process consists of advancing the continuous flight auger down to the desired tip elevation or depth or embedment into a bearing layer, or potentially to a refusal condition on maybe something that's very hard, like an intermediate geomaterial or a bedrock. After you attain that termination depth or termination criteria, the grout is then injected through the hollow stem of the auger. It is injected all the way down to the tip of the auger without extracting the auger. The cork or plug on the bottom of the auger is blown from the pressure that's induced inside of the continuous flight auger. A head of grout is built up above the tip of the auger, a specified amount based upon maybe a particular geology. The auger is then extracted in a controlled, methodical manner while continuously pumping grout, such that the incremental grout factors are in excess of theoretical. And this is coordinated in a controlled, methodical extraction manner all the way up to the ground surface, where the grout return is always seen in this drill technique, typically before the tip or bit of the auger exits the ground surface. And normally you see a buildup of the grout head such that you build up the grout on the way up and out of the hole. Once the continuous flight auger bit exits the hole, the grout is still obviously in a fluid state. The reinforcing cage is then lowered into the fluid grout, typically consists of an upper circular type arrangement of reinforcing steel with a single bar extending to the tip of the pile. That is inserted through this wet-filled grout column, typically with minimal effort, and that results in your completed reinforced grouted section that serves as your deep foundation element. So now I'm going to move into the first mini case history, which is regarding the Mercedes-Benz or Falcon Stadium. For those who may have attended SuperPile that just went by here in June, I had a more extensive presentation on the various foundation systems for the Mercedes-Benz Stadium. Today, we're going to focus on the auger cast in place pile system alone and the applicability of that to the specific areas of the stadium structure that were supported on this variable length auger cast in place pile system. So just a high level overview of the various different foundation systems that are beneath the Falcon Stadium or Mercedes-Benz Stadium. As you can see here, a myriad of colors. It was quite an interesting, fun project. We referred to this foundation concept as the patchwork quilt foundation system or concept, because there's quite a few foundation solutions, as you can imagine and see here, for this particular stadium support. On the inner bowl, essentially, we utilize shallow foundations with and without ground improvement. The outer bowl, more heavily loaded columns, as well as the mega columns, are supported on auger cast in place piles and drilled piers or drilled shafts. The retractable roof mega column support are predominantly on drilled piers or drilled shafts. However, some of the eastern mega columns for the retractable roof are supported on CFA or auger cast in place piles. This particular slide here shows you the subsurface conditions throughout the stadium footprint, focused on the south side of the stadium, going from west to east. And I really want to walk you through the stratification of the subsurface conditions encountered. We implemented SPT testing, rotary rock coring, cone penetrometer testing, surface geophysical techniques, downhole seismic testing with CPTs, dilatometer testing. So there's a whole myriad of different investigative techniques to come up with what we believe is in the ground, as well as the variability of what we anticipate in the ground. So starting from top to bottom, the gray depicted layer you see there, the first stratum, that is a uncontrolled urban fill layer. The tan depicted stratum, that is the residual soils or the residuum. The maroon depicted layer is what we're going to term the intermediate zone soils or the saprolitic soils. They're higher in SPTN value than the residuum. They have higher CPT tip resistances. They retain the relic rock fabric of the underlying subsurface materials, and they are typically a little bit more granular than the residuum. The residuum is on the border of essentially an SM to an ML. At this site, a little bit more on the SM side of things than the ML. Now proceeding below the maroon strata, you've got that sky blue stratum. The sky blue stratum is what's called partially weathered rock. The partially weathered rock at this site, the way we characterized it, was any material having an SPTN value greater than 50 blows per foot. Locally in Atlanta, that terminology is typically characterized by utilizing a minimum SPTN value of 100 blows per foot. However, for the purposes of this variable length system and delineating a intermediate geomaterial for frictional resistance, we back that criteria off a little bit to make use of that greater thickness of that layer compared to the 100 blow criteria. Below the sky blue layer is a green depicted strata, that is the bedrock. The bedrock at this site is amphibolite and biotite gneiss, mostly biotite gneiss with some amphibolite zones in various areas of the project site. This next slide shows you a similar look, but now this is a little bit outboard of the stadium in the southeast portion of the overall site. This particular profile you see here was for a bridge realignment that was necessary to route the roadway system around the south edge of the stadium. And as you can see here, very similar, again, color scheme a little bit different, but I think the big takeaway as you look at this slide is similar stratification. And what jumps off the page is that pinkish orange bedrock at the bottom and the variability of the depth to the bedrock, the variability of the depth to the tan layer, which is the partially weathered rock, which is that intermediate geomaterial, and also the absence of the bedrock in the middle of the bridge for that central bridge support where there really is no bedrock within a reasonable depth. And how would we deal with that from a design concept perspective? So moving into our initial thoughts, as I mentioned before, the auger cast and place pile solution was implemented for the outer bowl and the eastern mega columns. We utilized 18-inch diameter auger cast and place piles, having design compressive capacities on the order of 150 to 220 tons, reinforced as indicated here, with a range of grout strengths from 4,000 to 6,000 PSI, and two installation methodologies were initially proposed. The type 1 being a condition where we would install to refusal. The pile would be drilled through the fill, the residual soils, the saprolitic material, the PWR, and refuse on bedrock. The type 2 soils bedrock was at significant depth. We did not want to extend piles to that great depth, so we were looking at friction piles bearing within the intermediate geomaterials without a refusal condition. Important is capacity compatibility and settlement compatibility. Both type 1 and type 2 piles had the same capacity from a compression standpoint. There was some tension loads on these particular piles, relatively modest, somewhere in the order of 20 to 35 tons. So that needed to be taken into account as we looked at short stubby piles, if we were going to have short stubby piles at some locations. The next concept and vision was for the plaza structure. That is the structure excuse me, to the east of the stadium proper. And this particular structure, as we looked at it, there were some logistical constraints. There were some needs to up the diameter, increase the capacity, and have a smaller pile cap footprint. So we were envisioning 24-inch diameter piles having a capacity of 375 tons. Reinforcers indicated here, 6,000 PSI grout. Again, same approach, a type 1 and type 2, an end bearing pile, and then when bedrock was not within a reasonable depth, a friction pile. The bridge widening, as you remember, I presented before with that second subsurface stratigraphy. Here again, we're using piles similar to the Plaza, a little bit larger in diameter compared to the stadium proper, a little bit higher in capacity compared to the stadium proper. We did use GEC 8 as the framework for implementation of the AugerCast or CFA system below the bridge. That is FHWA's most recent guideline relative to the implementation of this pile type for bridge support. The piles were reinforced, as you can see here, 6,000 PSI grout, again, a type 1 and a type 2 approach. So key to success of the type 1 and type 2 concept was implementation of numerous pile load tests throughout various stadium quadrants, the Plaza and the bridge. The next several slides you're going to see are going to show the graphical representations of the pile load test results. So interesting here is a very short stubby pile, about 20 feet long, 18 inches in diameter, design capacities of 150 to 220 tons, ultimate capacities exceeding 550 tons. So certainly have a safety factor of 2 and have a very rigid response at the design loads for this short stubby end bearing pile on very competent Atlanta bedrock. The next installation category was what I mentioned, the type 2 pile. That is our friction pile in PWR. Again, a load test here ran out to a substantial load on the order of 550 tons. Again, factors of safety well in excess of 2 on both design loads of 150 or 220 tons. A little softer response is expected from the longer pile and the friction pile for the type 2 scenario. Moving on to the bridge load test, piles getting a little bit longer, bedrock getting deeper. This is a type 2 pile. You can see here again, a little bit more of a, I'll call it a less rigid response. This is a longer pile, heavier loaded element. We don't have end bearing within, or we don't have bedrock within a reasonable distance. So a friction pile, not an end bearing pile. Again, very good response. And we're showing here the geotechnical ultimate limit state criteria defined by GEC 8, substantiating an adequate safety factor per GEC 8. Now moving on into the end bearing pile within the bridge, a little more rigid response. Again, GEC 8's geotechnical ultimate limit state shown there as a failure criteria. We're well above that, satisfactory performance from a load carrying perspective. So now I want to just focus on the importance of production verification. And we hear a lot about the grouting phase, and we hear about the emphasis of AME and the value of it during the grouting phase. And by no means am I diminishing the value of AME. I fully support the AME system for the grouting phase. I think it's a phenomenal system. I think it adds a lot of value to what we review as engineers, what contractors are able to see real time. But I want to focus today on the drilling phase. And the reason I'm talking about the drilling phase is because that allows us to see that intermediate geomaterial when we encounter it, allows us to understand maybe the consistency or the hardness of that geomaterial, that intermediate geomaterial, and compare that to what was observed in the indicator and test pile program. So these next two slides, or this next slide, shows 2 individual records of AMEs from the job site, one on an 18-inch diameter pile on the right, and one on a 24-inch diameter pile on the left. The black line you can see where you see the depth on the one on the right, if you look at the graph on the one on the right, but all the way on the left side of the sheet on the right, you'll see that black penetration rate. You'll see from about 0 to 60 feet, you'll see a relatively rapid penetration into the ground. you'll see a transition zone and then a very slow penetration from about 65 to 90 feet below grade, indicative of encountering that intermediate geomaterial, that partially weathered rock. It's not always that easy to see it. So the AME record on the left for the 24-inch diameter pile, if you look at that black penetration rate, a little bit more difficult to see. It needs a little bit more study. We can also use what's called the KDK pressure, or an inference of torque, to help us combining the drill penetration rate with the increase in torque. That helps us have confidence that we're encountering the PWR and we're sufficiently embedded into PWR of adequate resistance. So these are very critical to our verification of those concepts I mentioned, the type 2 concepts specifically, where we're encountering that intermediate geomaterial, we're drilling sufficiently into it, and the intermediate geomaterial is of sufficient hardness, or we're inferring it's of sufficient consistency so that it's similar to our test pile conditions. Now moving into the second mini case history, which is a case study on a beachfront high-rise in South Florida. This is going to be a markedly different approach to the implementation of variable length and the efficiency of the auger cast in place pile system. This is conversely different than the Mercedes-Benz Stadium. What we're going to be talking about today is how to properly delineate a deep subsurface condition, and how to, through a phased extensive subsurface investigation, how to properly delineate that zone of poor subsurface conditions relative to the tower structure, and how to vary the lengths of the piles within the tower proper itself and achieve capacity and settlement compatibility. And I think you're going to see that as I walk you through the next several slides. So this slide shows the limit of the 24-story tower that was proposed for this beachfront project. This project is about 15 years or so old, so it's one I dug out of my archives, but I thought it was very interesting as we talk about this topic. The project includes a 7-story parking garage and a 5-story retail structure. The retail structure is on the east, the parking garage is on the south, the 24-story tower is on the north side and extends between the letter A, see there, all the way to the letter C. So it encompasses essentially that entire block from TB2 to B7, and from letter A to letter C on the subsurface profile. The clouded borings are the borings where the deep compressible subsurface condition was documented. And now I'm going to move into the next slide where you're going to see the subsurface conditions. I'll briefly talk about the subsurface conditions starting from the ground surface and extending deeper into the ground. Stratum 1 consisted of a layer of fill. Beneath that was a silty organic silt and peat deposit of various percentages of fines. That's our classical beachfront organic deposit that we see buried either underneath the fills or our beachfront granular soil deposits in this area of South Florida. Underlying that is stratum 3, which is a granular beachfront shelly sand. Below that is our first sedimentary rock layer that we encounter about elevation -10. And from about elevation -10 to the termination depth of the borings at about elevation -125, which is about 135 feet below grade, we're in and out of various degrees of cementation, but a sedimentary geologic limestone, calcareous sandstone, coconut limestone profile with interbedded intermixed zones of granular materials with varying degree of cementation. So a very complex subsurface profile relative to SPTN values, consistencies, and hardness. But interesting, down at about elevation -60 to about -70 is a very weakly cemented, very loose compressible subsurface deposit we labeled here as stratum 7A. That was about 10 to 12 feet in thickness, had single-digit blow counts in terms of SPTN values. We had some weight of rod, weight of hammer zones. So this is the deposit of concern as we think about large pile groups. If we think about supporting a 25-story structure above that zone, and would we get excessive settlement? So as we looked at our settlement analysis and considered the thickness of this deposit, the variability of it, we did indeed come to the conclusion that we could not support this very heavily loaded tower above this stratum where it's present. So as I mentioned before, we did this phased extensive subsurface investigation. You saw those borings, you saw the clouded borings where we did have the presence of stratum 7A. I want to move on this slide to the 16-inch diameter auger cast in place piles for the garage and retail. It was determined that the loads for those structures were not heavy enough to cause a settlement concern. So all of the piles for the garage and the retail structures that were 5, 6, 7 stories in height were supported above that compressible deposit when it was there or when it was absent, and settlement compatibility was calculated based upon the subsurface conditions and the loads of that particular structure. Conversely, that was not the case for the tower. The initial concept was 220-ton piles for the tower, reinforced as indicated in this slide, 7,000 PSI grout, 2 different installation criteria, one where the piles are medium length above, the stratum 7A is not present. The building was predicted to settle less than 1 inch. Then we have the condition where we've got that stratum 7A present. We need to bypass it. We need to get bearing at depth. We need to have settlement compatibility for this variable length pile foundation system. The concept was piles installed to elevation minus 85, bypassing stratum 7A. Here is the results of the load test. As you can see from here, a pile installed to about elevation minus 40, which is that medium length pile I talked about for the tower. We can get the capacity from the upper subsurface layers, but it's all about settlement compatibility when we're talking about this deep-seated compressible zone. It's all about proper delineation of where it's present and where it's not. So this was the concept that we came up with. About 100 piles or so were a medium length, saving about 45 feet in length in terms of those 100 piles, provided settlement compatibility is attained and provided that stratum 7A is not present. And that was our conclusion at the time when we generated this foundation concept plan. The piles shown in dark in black there with the colored in circles, those particular piles are our long foundation elements that extend to elevation minus 85. And within that zone of the tower, that stratum 7A was consistently present. So we had to bypass that weak compressible subsurface material to attain settlement compatibility between the medium length piles and the long piles. And indeed, we did obtain settlement compatibility. So this particular slide shows the foundation performance of the building 1 month after topping out the tower. Remember, the tower was 25 levels. This particular slide shows a snapshot 1 month after top out, but the way this data was obtained is we instrumented the shear walls and columns. And what we did is every 5 floors, we would survey the monitoring pins installed into the shear wall and the columns, these Tapcon type concrete nails or screws. We would survey those every 5 floors as the high-rise building was constructed. We would get a plot of basically settlement at each column or shear wall with the number of elevated levels, so we could react if we had to adverse performance. But fortunately, there was no adverse performance. As you can see from this information, the settlement is very compatible throughout the areas of the medium length, variable length foundation system and the long piles. And remember, we're talking about elevation minus 40 compared to elevation minus 85. And the settlements are less than 1 inch throughout the entire tower structure. And remember, I mentioned that we deemed that deep compressible subsurface material inconsequential relative to these reduced height structures. Indeed, that was the case as we measured the garage structures for movement as well. So I'm running a little bit short on time here, and I'm sure Gerald wants me to hurry up so you can get to the next presenter. So I'm going to quickly go through the conclusions. I hope that you agree with me and you see me illustrate that auger cast in place piles can provide an effective solution where we have highly variable foundation, highly variable bearing materials such as the Mercedes-Benz Stadium, where we have variable depth of bedrock, variable depth of partially weathered rock, or embedded deep compressible subsurface materials that requires proper pre-delineation so that we can have settlement compatibility. Multiple load tests are a must, especially at a condition like the Mercedes-Benz Stadium, where we've got variation in intermediate geomaterials, variation in depth of PWR, variation in bearing materials, type 1, type 2 piles. The automated monitoring equipment was essential to make sure that the production implementation was correct, could be validated and consistent with the results of the test piles, the indicator piles, and the results of our load test. And finally, I would encourage everybody on the call, if you're not doing this, please make a habit of getting that final performance data. What's the final thing we rely upon as engineers in terms of settlement compatibility is sharpening our pencil, getting better on every single project. And in my opinion, there's really nothing better than running those settlement calculations, coming up with that solution, implementing that solution, and then verifying the settlement performance of that structure with physical settlement monitoring, or maybe even further kinds of monitoring, such as strain gauges, other kinds of monitoring devices. So I would encourage everybody on this call to really think about performance monitoring as you look at your projects in the future. So with Gerald, I'll stop there. I'm about 2 or 3 minutes over, and I'll hand it back to you.
Thanks, Matt. And it's